This is our website for notes about maths, ZK, and ZKML. So if you go to maths.xtrp.io, the notes are there under the ZKML notes. All right. So I'm Laurence from Xtrp. If you want to contact us, here's some details, and yeah, there's a link to the notes as well. Thank you for coming early this morning after, I know, some good parties last night. All right, so what I'm going to talk about, I'll talk a little bit about the two technologies, so machine learning and ZK, to give you an introduction. Then we'll talk a little bit about the problems of bringing these two things together. And we'll go through some popular frameworks that have been invented. I'll talk about some of the latest developments. Demonstration, I can start that. I don't know if you want that, but we can have that. And where you can find out more information. Right. So I'll start about talking about machine learning. So it's part of the general area of artificial intelligence. And machine learning itself, there's a sort of subset of that, well, sort of more in-depth way of doing it, I guess, or more complex, called deep learning. So you'll see many of these terms, but machine learning is the more general one. And the idea behind it is that we start with some training data, and we teach our machine learning system on the training data, and then we hope that it can generalize and be able to use that the training to then make predictions or do something intelligent. So that's the hope. So when we're looking at machine learning, we have really two phases. We have a training phase where we're teaching the system, and then we have what is called an inference phase, which is where we're actually using that trained system to do something intelligent. And for some terminology, we talk about machine learning models. So these are the things that we build when we're training. We're creating these models, and the process of training can be quite complex, and it is quite time-consuming. And there's special hardware that is used to help with the training, just because it's so computationally intensive. It can take a very long time, and typically we use things like GPUs and things that will do parallel processing so that we can get the training done as quickly as possible. But even so, if you look at some of the latest machine learning models, such as the sort of the ChatGPT models, they have very, very expensive hardware, and they still take months to train. So it is an extremely involved, expensive, and long-running process. So yeah, these are the two parts really. So we do the training first of all, and then we can use that training to make some predictions or do something intelligent. And yeah, as I say, it can take a very long time. Now, one type of model that has been used for quite a long time and has been very successful is a thing called a neural network. And in concept, this is modeled, the architecture of it is modeled in a way that is similar to the way that the neurons work in the brain. And so what we have is a number of nodes or neurons, if you like, and they're created in layers. So we have layers, an input layer, what's called a hidden layer, and then an output. And there may be many, many hidden layers. So this thing may be many layers wide. And after this has been trained, what we will do is we will provide it with some input in these input layers. And these nodes will pass some signals to the next layer. And as you see, each node will have connections to many other nodes in the next layer. And then those nodes will pass information to the next layer, and so on until you get some output. And then hopefully that output is something sensible. And as I say, the hidden layer here, there could be many, many of these. Right. Now, to go into a little bit more detail, the way that we actually get the intelligence in there, the configuration in there, is that these nodes, when they're sending signals, these signals can have what are called weights. So each link between, let me go back. So each link that we have here between a node and the next layer will have a weight which will show what proportion of the signal from here will go to each of these nodes. And we adjust these weights, and really that is what the training is about. It is getting these weights created so that something useful will happen. So if we look in more detail at that, we have our inputs to a particular a node or to a layer, and then there will be weights which will do a proportion of this input and then send that to the next node. And so all of that, one node in the next layer will have inputs from many nodes in the previous layer. Those all get added together, so that's what the sigma is for. And then that is further processed in what is called an activation function. So what this activation function is doing is trying to decide what to do, what to pass on to the next layer. And you could have it very simple. You could say, well, there's going to be a threshold, so that if the values we get here are above a certain level, then we'll send a signal to the next layer. But if it's below a certain level, then we won't. Okay, so that's one thing you can do. But what usually happens with these activation functions is that they are more complex. So they will send maybe a little bit of signal if this signal isn't very strong, and then it will gradually increase until there's a great signal as these are greater. But these functions can be quite complex in what they look like. Please come in. Please join. Okay. All right. So another point we get with neural networks, we also have these things called biases, which is really an extra switch we can add to a particular node to perhaps to make it fire more often, to make it pass on signals more often. And this is just set as part of the architecture. It doesn't depend on the inputs here. It's just always going to give a certain value as well. So this is a way you could say, okay, this particular node we think is really important, so we're going to give it an extra kind of a boost in the signal, and you set that. But it doesn't depend upon the signal it's receiving. Okay. And that's really how neural networks are built, but they're built with many layers, and that's how they work in terms of going in this direction, where you start off with your inputs and you do the processing and get to some outputs, or maybe this is the better model. You start here and you do the processing and get to some output. So that's called the inference stage. That's where we're doing something useful and hopefully intelligent. When we want to train it, though, what we do is we go in the opposite direction. So when we're training a model and we're trying to work out which weights are actually going to be useful, what we do is we say, okay, well, I know what output I want. So, for example, if you're training your model so that it recognizes a picture as being either a flower or a car, then what you can do is you can say, okay, if I know the output is, I want it to be a flower, I want it to tell me that this is a flower. You can provide it with some inputs and then see what happens. And if it gives the correct output, then you know that the weights you're using are correct. And you can just keep going through adjusting these weights until it gives you the correct output with the input that you have. Okay. But that process of correcting these weights, again, is quite complicated, and it takes a long time. But that's what we do. Okay. And so that was a basic neural network, and these were invented maybe, 30 years ago, something like that. And then people started to make them more complicated, and we get things called convolutional neural networks. Convolutional just means we're changing things in some way, we're doing a transformation. And I won't go through all of this, we don't really need it, but this diagram is a little small, a bit bigger. But what we do to get things that will work and be actually useful, we build models that have very many layers. So you've got your inputs here. This is a picture of a robot, and it's going through many, many layers until you get an output. And the output will be saying, this is a robot, and it's not a flower, and it's not a car. And so we have lots of layers. But then the other thing we want to do is when we have this picture, we don't want it to be too sensitive to to a particular pixel in the input. For example, if I took this robot, like the actual image, and just moved it up slightly, it should still be recognized as a robot. We shouldn't be completely dependent on there being, an eye at a certain point, a certain coordinate. And so with convolutional neural networks, what they manage to do by doing many transformations in these layers is to extract features and work out, oh, this thing here is an eye, and I don't really care whereabouts in the picture it is. I can recognize that as a feature, wherever it is. So this is a way of just making our networks even more sophisticated. Okay. And we can also have these things, we have things called dropout layers as well, where we can say, okay, we're going to ignore some part of the picture or ignore certain features because they're not very useful. And another design that was tried is a thing called recurrent neural networks. And the flow of this is I'm going from bottom to top here. And the recurrence part is the fact that we can get some flow going sort of back through the layer. So it goes into the hidden layer and it can go across, and then we can also get input back, maybe not to the input layer, but perhaps to other hidden layers. So you get kind of loops being involved in the layers. And what this is showing is an example where we're typing in some characters and is trying to predict what the next character should be. So as you can see, we've started typing in at the beginning of hello, and it's coming out saying, okay, the next one's going to be the rest of this word, and we've got the final letter there. And these were quite successful, and I played around with these a little bit. You could, about 10 years ago, they were invented, and you could train these on kind of normal PCs, normal hardware, and they did quite interesting things. For example, this is a bit small, but you could train them on some text, and then it would produce something similar. So, for example, you could train it, give it some Shakespeare, and then just give it a letter, and then it starts to produce something that looks like Shakespeare. So this is an example that it produced by itself. And it understands that there are, for example, characters, and it will have a character that is going to speak, and then it will print out what they're meant to be saying. So it's quite successful, quite sophisticated. And this is similar to what ChatGPT is able to do, although that uses a different technology. But, so ChatGPT, these are large language models, and what's really happened with these is that you've got this idea of the neural network and you've made it massive. And so the number of weights involved, as you can see there, is 1.75 billion weights, and they've got this network of 400 layers. So it's these things are absolutely huge. So you can imagine when you're training these and you've got to set up all these billions of weights, it's going to take a long time. All right, now, some of the questions about this. This was originally, this talk was also about privacy, and one of the reasons that we put together machine learning and zero knowledge is because we want privacy. And these are some of the reasons why we would want to do that. So, for example, if we're building one of these models that we're going to use, it could be that for trained data could be very useful. And so we may not want to have to share that. Similarly, when we're training these models, the input to these models may be sensitive. So we may not want that to be public. And when we're using these models, the inputs could be confidential or personal. You could have a model that is using medical data to predict something. So you have to be careful then that data is not leaking. So there is the need when we're using these machine learning models that we would want some privacy and we don't want to necessarily share all of the data. Now, question, you could get around this because you could just use your model locally. You could just do everything in private. So if you're a company, you could train your model on your own data. You could just run the model yourself and not let any of the data leak out. So everything would be private. But then you get one point, the second point here is useful to learn from other models. It's useful to be able to use training that other people have done. So we would like to be able to share these things. Also, and this is another aspect of the ZK ML, is that we often want to verify that this model has worked, because if you give some data, say you give some medical data to a model, and it comes back to say, yes, you're fine, you don't have a particular disease, well, obviously that's good news. But then, would you trust them? Do you know that they've used a good enough model to do that? Because they could have used their super cheap, very simple model that always comes back to say everything's fine. So it would be nice is if you could verify that the model they used was a competent model, was correct, and was doing the computation correctly. And so this is another reason why we try to get ZK and ML together. So to move on to ZK, this technology, sort of an aspect of cryptography, it has two particular useful features. One is that we can verify computation. So if we have some computation being done, we can create a proof that that was done correctly. And the checking of that proof is very quick. So if I have a computation that lasts 10 years, I could check that that computation was correct in a couple of seconds. Okay, which seems too good to be true, but it's true. The other good point is that we have some privacy in zero-knowledge proof. So that's the zero-knowledge aspect. So we can put in private inputs to our proof, and the person who's verifying the proof doesn't get to know those private inputs. And the process of doing zero-knowledge proofs is a number of transformations. We start off usually with some high-level language. We write some program, and there's some examples here. This then gets turned into what is called a circuit, some representation of the higher level language. And then that goes on, we do further things. And this is really part of the setup. And what it allows us to do is to provide some inputs and be a public input and a private input to the system we've set up. And this will create a proof for us. To go into that in a little more detail, this is an example of the real world and Snark world, and I'd like to live in Snark world. This is really where we do the setup. So we create the circuit from maybe a higher level representation, and this feeds into the setup. And once we have that, we can use the setup along with the private inputs, the witness, and any public inputs to go to something to create a proof. This creates the proof, which can be sent to something to verify that proof. And then maybe you would pass that on to some other aspect of the system, maybe a blockchain, whatever. I think maybe I'll skip through some of these, and we can perhaps have more time for questions. So I'll talk generally now about how we've managed to put these two areas together and what projects are out there. So this is still a very new area, but there are things being built. So on the left-hand side, we've got companies that are building hardware to help accelerate this process. So this is because the training takes a long time. So these companies are building stuff that will help that training be quicker. These projects here are ones I'm going to talk about in a second, where they actually allow you to do the process, and they will take models and allow you to get some output from the model with maybe private inputs. These are more about blockchain generally, or things like Axiom, that is allowing you to look at things that happen on blockchain and prove that that was correct. This decentralized training, the Federation of Machine Learning, I'll come on to a little bit later. This is really kind of a different area, well, or an alternative to some of the ZK side. These ones, again, some of them are a little different or using other technologies also. Zama is a company that is doing quite a lot, but they use a cryptography, a technique called fully homomorphic encryption to allow private inputs to their processes. And then for some of the use cases, you may have heard of WorldCoin. They have these things called orbs, which they take a scan of your retina and then will give you an identity based on that you can then use. And they claim, and I'm not disputing this, but they claim that they delete the data and they just have the identity, so there's nothing can be traced back to you or to your biometric data. And they're doing quite a lot of work on the ZKML side. They're doing a lot of research on that in that area. Other things, I'll talk about this one, which is a standard for NFTs, where if you create an NFT and you're generating the image using AI, so using the sort of the typical tools we can use to generate images, then this is a standard on Ethereum to check that that image is how that has been generated and that it belongs to this particular NFT. And then Rockybot is, or it was, an online trading bot. So it had some intelligence and it was let loose on, I can't remember which chain, and then it just traded and it was hopefully made a profit. It did make a bit of a profit, I think. But you could check what it was doing by the ZK side. I don't know if I do have some slides about Rockybot somewhere, but I don't know if I got them in this presentation. All right, so I've talked about the two areas of technology, and you might think, well, great, they're both interesting, and wouldn't we love to just put these together? And why wouldn't we? And what problems would we have? Well, there's a lot of problems. Some of them, first thing is the complexity. So both of these areas are complex areas and require people to understand these areas in a lot of depth. I guess on the machine learning side, maybe people have been aware of this for longer, but it's still a very complex area. There's still not so many people who understand it. On the ZK side, it's a very complex area. Very few people understand it. They're still developing the area. So that's one of the first problems. It requires a lot of knowledge. Also, the one thing with one of these neural networks, if I presented one of them to you and said, here, this is capable of translating from English into French, and you looked at the actual model and you just see lots of weights, and it's difficult to understand, well, where in all of that is the ability to do what it can do. It's very difficult to understand how machine learning models actually work. We know kind of what they're doing, each signal going to the next layer, but where is the intelligence in that? It's somewhere within those weights and it's somewhere within the architecture, but how that actually works, how it's actually manifested into something intelligent and useful, we can't readily see. We can't readily sort of point at it and say, okay, that's the bit that's doing a certain thing. We just, yeah, it's very difficult to work that out. But other problems with integrating these things, one of the biggest problems is that they depend upon a fundamentally different type of maths. So with machine learning, we're using floating point representation. So we're using fractional numbers. We're using, decimal point and then, lots of decimal places. And we also do a thing, we tend to use matrices. It's a particular type of operation. With ZK, we can't use floating points at all. We just use integers. We tend not to use matrices either. So the types of operations that are involved in each of them are fundamentally very different, and it's very difficult to get these two areas together. And on this floating point aspect, you could say, well, one way we could turn that floating point into a whole number. So if I have, number 3.7, I could make that into a whole number by multiplying by 10. So I get 37. I just have to remember that I've multiplied it by 10. So we could turn it into an integer, but that adds an extra step into our processing. So if you're having to do that to every number in the system, that's going to increase the time taken to do everything. The other thing you can do, and we do this in machine learning as well, is you can reduce the precision of the numbers. So you could actually reduce and get rid of some of the floating point numbers anyway, and just cut off after the decimal point. And this does work, but after a time, it makes your model less accurate. You're losing accuracy by doing that. So it's not a perfect thing. So that's one of the major problems. But some of this is improving over time, and there are tools to try to do perhaps some of these conversions. And then the final point here, which I'll come back to with this project, is looking at a completely different way of doing machine learning, which integrates more easily with ZK. Another aspect that we have problems with is that there's two parts really. When we represent floating point numbers in computers, they don't work completely accurately. And you can try examples of this. You can do addition in maybe in JavaScript with floating point numbers, and sometimes they come up with the wrong answer just because floating points are not represented very well in the hardware. And similarly, with the way that we train the neural networks, we often use randomness in the way that we're doing it, and that doesn't work well with zero knowledge proofs either. So that's another stumbling block that we have. I really like this quote that reality has a surprising amount of detail, and that's really the heart of the problem, that we're trying to get all of that detail and put it into something that wants to be much more discrete, and that is a fundamentally difficult thing to do. Okay, but let's not give up. We are making we are getting there, and as you saw from the ecosystem, there are projects that can do this to some extent. Where we have really got to is that we can do the inference stage. So in ZK ML, we can start with some input, and we can start with a model that's already been trained, and then prove that the computation from the input to the output is correct. So we can do that. That's kind of where we're at. Training is much more difficult because that's much more intensive, and so that is still much more of a problem. Okay. This is just an example. There's one project called TensorPlonk, but this diagram illustrates the kind of thing that we may want to do, in that we could have someone who's providing machine learning for us. So we don't have the computational power ourselves to do it. So what we want to do is send off an input and get them to do the machine learning part and do the inference. But we want, and they've already got the weights, etc. But we want to know that what they've done is correct. So similar to what I was saying about the medical example. So you send your inputs to them, the provider, and they come back with some output, but they produce a proof, and then you can verify that proof that that was done correctly. So this is just a representation of what I said earlier. Okay. I'll skip through some of this, but what it's really saying is that it's looking at the problems we have. So if we have we're trying to build a neural network, but we want to do that using zero knowledge. And oddly enough, the neural networks themselves, that kind of architecture, right? Just go back to that diagram. So this kind of architecture is similar in some ways to what the heart of ZK looks like, or hearts of ZK models look like. In that in ZK we create these things called circuits, where we have gates, where we're passing, or where we're checking signals that could go between those gates. And so in some ways it looks very similar. So you might think, well, what we could do is replace these nodes by these gates that are what we use in ZK anyway, and then that would give us a circuit. It would look very similar to this. But unfortunately, that doesn't work because it's really from a performance point of view, it just would take far too long to do that. Which is what this top point is about. So the performance of just doing it in a very naive way is just hopeless. It wouldn't work. But people have, these other things here are just approaches that other people have taken to just chip away really at some of the problems and try to work at and see if they can put in little optimizations that will help us do this. All right. Now, I'll just quickly mention this. Onyx is a framework that allows people to share the architecture of a machine learning model. So it specifies what the nodes look like, the number of layers, etc. And it also you can specify the weights within the model. So it's a way that we can sort of abstract out the details of the model and then share. That's the standard that we can use. And this is being used also in ZKML. So some of the frameworks are available. There's one called Ezekiel, which is a library that you can use to take a model. It will get the details of that. It will build the file, the Onyx file, so it's in a standard format. And then it can create a circuit, so it can create the ZK version of that model. And then you can use that to put in some inputs, and it will run the machine learning, and you'll get the output, but you can then also get a proof that it was done correctly. And you can put in private inputs, etc. Another framework is Orion. So this uses Onyx, so uses that standard, and it allows us to create circuits with a type of ZK called a STARK. Okay, so there are different types of zero-knowledge proving systems. We have SNARKs and STARKs, and so this one is used for STARKs. And there's it's an open source project, and there's lots of resources you can use. And it is in fact then part of this project, which takes that, Giza takes that runtime and then adds tools around it to automate the flow that you will have through if you're doing machine learning. So it will be using the model, and you can automate the different processes using the Orion engine, but writing scripts around it, etc. So it's there to make the whole thing a bit more user-friendly. They also have data sets you can use as well. So there are standard data sets that are used for training, so they provide those also. I won't go through this. This is just more about Giza, but it really just shows the same thing. Or this actually. So this is Orion working, and you can use different libraries. So you can use Ezekiel, but also because it's doing Starks, you can write Cairo programs. So you can run a Cairo program, do some machine learning in a Cairo contract on StarkNet, and then have that proved with Giza. Okay. Let me move on. So to go through some more use cases, one very interesting one is around the authenticity of some type of media. Could be images or video or audio. And there was this example, the ZK microphone, which came out of a hackathon. And what they did is they took a microphone just like this one, and they stuck a Raspberry Pi on it. And what they would do is take the audio from the microphone and then sort of fingerprint that. And then you could create proofs that that hadn't been tampered with. And there was an example, a good example, if you want to dig into it, was with a podcast. So there's a podcast called the Zero Knowledge Podcast, which is well worth listening to. And one thing they did on that podcast was to build an AI agent so that you could ask questions and it would come back in the voice of one of the presenters. Okay, so it was an artificial voice being used. So on that podcast, then they got the person who invented or was working on the ZK microphone, and they recorded the podcast, and then they took the audio from that and they removed the background noise, but they created a proof that the resulting audio was genuine. So all that had happened to it was to reduce the background noise. They didn't change the voices or anything else. And there was a proof that that had happened. So that's to show that you can take some media and you can alter it, but prove what alterations you did. And similarly, we can do this with cameras. So there are some cameras that are built that have a hardware component that will fingerprint the image. But what you can do then is to take that image and maybe transform it, maybe crop it or rotate it. And you can have a proof that that is all that was done to that image, that it wasn't faked in any other way. So it's quite nice that although AI has given us the ability to create fake images, and which is problematic because now we can't really believe any image that we look at. We can't believe it's true. But also, where you can use the similar technology then to be able to prove that these are genuine. So it's quite a nice feature. Okay, so this is the thing I was talking about for the NFT. So the diagram sort of explains it best. So the idea is that we will have a user and they will be creating an NFT using AI-generated content. So to do that, they will create a prompt. So they will say, a photorealistic picture of a dog standing on a ball or something like that, which will then create some image. But what we can do is we can create proofs that this has been done correctly by showing that the proof did indeed lead to this particular image. And we can get the ZKML prover to create the proof of that. And then that can then all tie in to the actual NFT. So you can do this process, and only if it's verified that this image did come from that prompt would it allow the NFT to be minted, and then that would all be done in a smart contract, which could be verified there. So it's a way to verify that the image did come from a particular prompt. Okay, and so this is really this is just a standard that they've written for this. Okay, so I said we've got all these problems with putting together ZKML, and one project that came out of a hackathon about 18 months ago was Zero Gravity. And what they did is to say, well, yes, we've got all these problems because the way that machine learning works using neural networks and using weights etc., is really hard to integrate with ZK. And so what they've done is they found that there is a different way of doing neural networks. You can do these weightless neural networks, which don't work in the same way. They don't have the same weights, so you don't have this problem of the floating point operations. You don't have to do matrices, etc. It uses a different type of technology, which works better with ZK. There's more details there, but I don't know so much about it, so I can't really explain it much further than that. But there's links to the paper there if you're interested. Okay, so that's promising that they've got that. Okay, and then if you feel that I've been too gloomy about this and it's all hopeless and we're never going to get anywhere, there was something that happened earlier this year that was quite reassuring, quite uplifting, in that a particular project actually managed to work with one of the versions of ChatGPT. So ChatGPT obviously is seen as the sort of flagship machine learning model. And they managed to create a proof of that working. So they actually managed to do ZKML with that. And it was a previous version, so it was GPT-2, but still it had 1.5 billion parameters or weights, if you prefer, in it, which the billion mark is seen as something is seen as an important point. Once you get past that, you're seen as doing something useful. So it was important that we've got past that. We've managed to build a model that can prove this. It wasn't simple. So you've got details here of how long it took. So to actually do the setup, so to take that model, to create the circuit from it, took 91 hours on a 128 core machine with 1 terabyte of RAM. So not a laptop. The keys, or this setup produced things called keys. They took 10 terabytes, so the whole setup was big. And then that was just a setup. Then to create a proof, when they did it, it took 90 hours again to put in an input and get a proof that that had been done correctly. So they managed to do it, and it was seen as something of a landmark that they'd managed to do it. But obviously it took a time. But this is reassuring. We are making progress, and hopefully we'll continue to do that. We'll build upon the techniques they use. So it was Modulus Labs that did this, and hopefully the people can build upon those techniques, and we'll be able to get closer to the latest versions of ChatGPT. This is an example of, I think this is about GPT generally. So you're seeing the type, the amounts that are being spent for this. So it is a huge amount that is needed to do these processes. How am I doing for time? Okay. So that's ZKML. Now, if you know your scalability, your blockchain scalability, and you know rollups, you'll know that rollups, there are two types. There's the ZK type, and then there's the optimistic type. And so people, I'm guessing, they took that idea and said, well, ZKML is one approach. Why don't we do optimistic ML as a different approach? And that's what they've done. So we have this thing, optimistic machine learning, OPML, and it takes a similar type of idea to the way that optimistic rollups work, in that they do the inference, they do the computation, but they're just optimistic about it and say, we think it probably worked all right. If not, there's a possibility that you can challenge it, and you can then create a proof that it was done incorrectly. In order for this process, this verification game to work, you do need incentives, you do need this to be done on the blockchain, and you do need stakes to be there as well. But still, it is possible. There are projects building on this as well. And this gives and shows you the differences between the two types of approaches. So we've got more options there. Other things, federated machine learning has been around for quite a long time, and it's trying to do a similar thing perhaps to ZKML, in that it's what it wants to do is to be able to allow people to share data. So if you're training your model on a certain data set, what it allows you to do is to share that model with other people, and allow multiple people to train their models and share the data, but without giving away that data, without sort of leaking privacy. So it's a different way of doing it. One company I know called Flower AI who do this, and there's details of them there if you want to know more about it. But this is a little bit more established. This has been around for longer, but it's doing a similar thing to what ZKML wants to do. And federated machine learning generally is a more mature area, and there's some links there to that. I can do a quick demo, but of this. You can try this yourself. Really, the demo itself, in this case, not very big. But what it's doing, all you need to do for this demo is it's in a notebook already, and you just click these pieces here. Okay, it's not going to let. I need to sign in first. Okay, you can just click through. It's got all of the code ready, so you can just click through these areas, and it will take a simple model and eventually create a proof of it. So you can see, for example, if I go down to the end here, we've got the final stages here are generating a proof and then verifying the proof. So that's using that's Ezekiel using some standard machine learning models. Okay, so if you're interested, other places, other resources. So DC Builder is one of the researchers at WorldCoin. He does a lot of talks and has a lot of resources in this area, so check those out. Yeah, WorldCoin generally are doing a lot of work on this. They've got repos. The Zero Knowledge podcast I've mentioned is good generally, always good to listen to. There's some further papers here. There's a community on Telegram you can join. The Ethereum Foundation have a team that are also involved in researching this. Please join our Discord server because we are going to be running a course later this year about ZKML. So you'll be able to get details of that. And we have further resources and courses available on our education site. Okay, that's everything. Thank you for coming. And I appreciate it was very early for you. But yeah, thanks for attending the talk. I hope that was useful. Thank you.